Good morning. My name is Fahad Ejaz, and I'm one of the researchers at the ComNet's research group of Aachen University of Technology in Germany. Today, I'll be talking about the resource-oriented mobile web server for long-lived services. So we will see what I mean by resource-oriented and mobile web server, and also what are long-lived services. So in the first phase, let me give you a brief outline of this talk. So we'll talk about research scope and the problem statement, and then I'll give you the concept of service as a resource and how it can be used to develop an efficient and optimized mobile web server architecture. And we'll see some performance evaluation results, and also I'll conclude my presentation at the end. Moving on to the research scope, what we have currently in today's world, we have web servers everywhere. So they're giving us and provisioning private data, multimedia websites. They're offering us to host these things on web server. However, they're also hosting certain things which are called web services. These web services are specialized software components. They perform certain application-specific functionalities, and these are accessed by certain types of clients. They could be mobile clients, they could be high-end laptops or machines or anything, and this access is transparent to them. This means these clients are oblivious to the fact that what are they accessing. They could be responded by a web service or by a certain website or anything else, any other software component, and they just know how to consume this data. So what we did is we defined this concept of web servers for the mobile nodes, and we brought these as a concept of mobile web servers in 2003, which was the first time ever. And in this mobile web server concept, what we do is we host certain web services. We call these web services mobile web services. When two mobile web servers are providing services to each other, we call them peer-to-peer mobile web services, or in general, just mobile web services. The benefit is we are able to access to mobile nodes remotely over the internet from anywhere in the world. And it uses the same service-oriented architecture concept, where the broker is used to publish the web services and the SOAP protocol is used to consume the services. So based on this web service concept, what we did is we defined certain asynchronous interaction patterns. In the first phase, the client requests the service over a certain network infrastructure from the mobile server, and the mobile server either invokes it or schedules it for the invocation. However, whatever happens, the server acknowledges the client that your request has been arrived, and the client is transitioned out of the block state. When the service performs its task, it is performing in a long-lived fashion. And when the tasks are finished or it wants to send certain periodic update, it contacts the client back, and the client acknowledges the update by sending a response. So this is some sort of reliable kind of communication in case of request response and solicit response. The important point is these requests and response and solicit response are not just coming out of the blue. They are the standards specified in the web service description language. These services are long running. They could run for years and months or days or hours, depending upon the application requirements. The benefit is we can consume the service and receive a response on two different network infrastructures. It also supports service management because we can control and monitor the service. We can, of course, make the service invocation immediate and scheduled based on the requirements. And the server is able to reach the client because they both exchange the endpoint references while they communicate initially. So it is some sort of reliable and standardized interaction model that we have derived here. Based on this model, we define a problem statement. What currently mobile nodes are doing is they're using SOAP messages to consume web services. So SOAP makes mobile clients very thick because it's activity oriented, only based on XML, and with the increasing web service standards integrated inside a SOAP message, its payload is increased quite a lot. And the processing overhead at the server end as well as at the client end, it's quite a lot increased. So we want to opt it in a way that we have clients which are thin clients, and they can access the resources on the internet just like any resource we do access today in the internet. It should be format neutral, not only dependent on XML, and we would like to access web services just like any World Wide Web access. So this should also make the server lightweight as well as the client lightweight. So this is the issue we are trying to solve here. What could be done? So what we came up with was the idea of service as a resource. so that we can have fast and simple remote access nodes, and we can also optimize the performance. So with this concept, what we could do is we could identify two fundamental principles to access service as a resource. So this is based on the URL and the HTTP method. You use URLs to access a service, and you define HTTP methods to convey the semantics of that service. This is also called REST, Representational State Transfer. So in the representation, we have currently HTML or XML or JPEG or any format or any resource existing on the network. State is the state of the client in which it transitions after this representation has arrived, and transfer is the HTTP protocol that we currently use. This REST is not a standard, but it uses standards like URL and HTTP. It's similar to the client-server architecture, which is also not a standard, but it's widely used as a matured approach. The biggest example of this REST architecture is the World Wide Web. Because, for example, what we do is, this is the URL of my personal homepage on my research group website. So this is the representation. This HTML file is the representation of my information. This entire URL brings my browser in a certain state when this representation is arrived at my PC. And this HTTP protocol is used for the transferring of this information. So that's how the World Wide Web works today. So we want to apply the same concept to the web services. So what we did is we defined URLs for web services. So since we are talking about long-lived web services, which are also called asynchronous web services, we define a URL to access services. These URLs are contains IP port, of course uses HTTP because REST relies on HTTP. And we mentioned the service name. For example, we want to look up the GPS location service, and it's a service of type asynchronous. It should be started by the component factory by invoking its method called create instance. That's the URL that we specify, and that helps the mobile web server to understand what method it should be invoking without parsing any big XML documents. However, this URL does not give any idea to this GPN location service what actually it should do. It should either fetch something for me, update something, insert, delete, or what. So for this reason, we define HTTP method mappings for these services. So if I map this URL with the get method, this service will fetch me something. The post will tell this service to update the records. Put will insert it, and delete mapping will delete certain GPS coordinates or locations from this service's records. So what we are trying to do here is we are trying to use HTTP methods for the service to identify their own actions and semantics. The service provider, while developing this service, specifies which actions service should perform on which method. And the server only manipulates the URL, not the service payload. So this makes the server very lightweight. So we took this concept and we defined an entire architecture. In this architecture, there are certain components. It looks complex. I'll try to explain in as simple way as possible. So we have a request. When it arrives, the server identifies if it's a REST request. Assuming if it's a REST request, it is delegated to a component which is called the REST manager. This REST manager component is responsible for extracting the information inside this request and creating a component that is called a REST container. This REST container contains all the information of this request so that we can exchange this component, this object within the server architecture, so that we don't have to parse the request again and again. Once this REST container is created, the request flow arrives back to this initial component who checked the REST request, and this delegates the request to another component which is called the asynchronous manager. Asynchronous manager is responsible for identifying which server endpoint should receive this request. There are 3 server endpoints: service factory, service observer, and service instance. So in this case, we have service factory who is responsible for creating certain service instances and invoking the services. So this is given to the service factory, and the service factory creates a service instance. Service instance stands behind the asynchronous long-lived mobile web services to provide the ability to be managed. So you use service instance to manage this service in terms of control or monitoring. When this instance is created, the client is instantly notified, and that this completes the service creation process. And that's the first phase of that asynchronous interaction where we are talking about request and response. After that, the service instance gives the flow to the deployment manager, who is responsible for searching for the service, looking up the service, and starting the service in either a running state or immediate or the scheduled state, depending upon what client has specified. And once this is done, this process is called the invocation process of the service. Assuming the service immediately starts to run, it executes its functionality and identifies its resource actions and semantics based on the HTTP method mapping that we receive with the URL. And once it is done with the functions that it was supposed to perform, it gives the result back to the request processor, and that's where the service execution phase ends. After that, the request processor makes use of the response processor to send the response back to the client, and this is where the solicit response takes place from that asynchronous interaction diagram that I initially showed you. So with this architecture, we did some performance measurements, and we saw mean server processing latencies of SOAP, and we also compared with the REST server processing latencies for the service creation process, the initial request response cycle, if you remember. So we saw that there was a significant improvement in the mean latency with the REST architecture. So it was approximately 79% faster than the SOAP architecture. And there's an interesting thing to note here is we calculated standard deviations based on these mean values, and we came to realize that the minimum amount of time required by the SOAP server is actually more than the maximum amount of time required by the REST server. So that's really interesting and a good performance improvement. We also tried to measure server component latencies. In these server component latencies, we also compared them with the REST server component latencies, although we included some new server components for REST architecture, but we were pleased to see the good performance improvement in case of REST. And there was an interesting fact that we noticed that the individual server latencies here individual component latencies here, were more than the latencies of the REST server as a whole. So this is the complete time required by the complete REST processing, and this is the time required by one component of the SOAP architecture. So that's really interesting, and it's a good performance improvement with the REST architecture. This is actually the resource-oriented access of mobile web services, which are long-lived in the web server architecture. And we identified the reason for that, and that was the SOAP parsing. We were able to avoid a lot of SOAP parsing, and that resulted in significant performance improvements. We also checked for the server utilization, and we came to know that with the SOAP architecture, with approximately 35 requests per second, the server utilization reached more than 90%, and with the REST architecture, it was 180 requests per second, and the utilization was less than 90%. We used queuing theory to model these server utilization characteristics, and this is a significant increase in capacity. And we can easily say that the REST architecture is able to offer more than 200 requests per second easily for the long-lived services. So we are pleased to see such results.